Okay, so now this is not something I expect you to copy down right now. Okay, section 7.2 deals with what are called direction fields and Euler's method. Euler's method we'll get to on Wednesday, but let's talk about direction fields. So let's see what we have here. Now, we have, let me get my stylus here. We have 4 differential equations and 4 pictures here, and these pictures are known as direction fields. And what direction fields are they are graphs of tangent lines that obey the direction field. So let me just give you an example here. Let me go to the whiteboard. Let's look at this first differential equation, y prime equals 2 minus y. Okay, let's take a look at that. All right, so let me clear this. Y prime equals 2 minus y. Okay, so now what I'm going to do is I'm going to draw here an x-axis I don't know why I have trouble doing this. I'm going to draw an x-axis and I'm going to draw a y-axis. And I'm going to put a few values here. Okay. And okay, so I want to say this the right way. So, you know, this is the right-hand side of the differential equation. And y prime equals 2 minus y. That means also that dy dx equals 2 minus y. Now, suppose y equals 0. If y equals 0, what does this tell you about y prime? What would y prime equal when y equals, I'm sorry, I want to say when y equals, hold on. One moment. Let's say y equals 2. Then what does y prime equal? That's right, Victoria, it equals 0. Because y prime is 2 minus 2, and that equals 0. So this means that for any coordinate where the y coordinate is 2, okay, for any coordinate where the y coordinate is 2, the derivative of y with respect to x is 0. And so that means that tangent lines are horizontal along the line y equals 2. Okay. If the derivative is 0 along the line y equals 2, that means you have, well, the derivative of, I'm sorry, I want to say this the right way. If the derivative is 0, that means the slope is 0, right? And the slope is 0 when you have a horizontal, for a horizontal tangent line. So far, are we okay? All right. Well, let's take a look. Let's take a look at another value of y. Let's take a look at another value of y. Let's say that let's say that let's suppose that y equals 1. Okay, well, y equals 1 implies that y prime would equal 2 minus 1, and that's 1, right? So this means if we were to, hold on here now. Yeah, if we were to pick values here, okay, where coordinates where y equals 1, and we were to draw tangent lines, the tangent lines would have slope of 1. See that? All those coordinates there have a y coordinate of 1, and their slopes are equal to 1. Please let me know if you have any questions so far. Please let me know if you have any questions so far. All right. Well, let's go ahead and pick y equals 3. So I'm just picking some values. Let's suppose y equals 3. Well, y equals 3, what would the derivative be for that value? Well, the derivative, y prime, would be 2 minus 3. That's right. Good, Clay. Minus 1. Okay. And so, again, if we pick some values here, you know, I'm gonna just pick some points in the xy plane whose y coordinate is 3. I don't care about the x coordinate. Y is equal to 3 for all those points, and their slopes are negative 1. So you see how I'm constructing the direction field? You see that? This is how you construct a direction field. Are there any questions? And incidentally, well, I should ask, are there any questions? Let me give a little more pause on that before you, you know, before I move on. Okay, well, now you might wonder, why is this direction field important? How is this useful to us? Well, let me show you. Let me show you. Let's say I wanted a solution to the differential equation here. I wanted a solution that was going to pass through the point 0, 3. Well, the solution has to follow the direction field. You see, any solution, all solutions have to obey the direction field. So, like, for instance, this point here, the solution that passes through the point 0, 1, it has to have a tangent at that point that has a slope of 1. And the tangent line, the tangent in the direction field, determines how the solution behaves. Any solution that you draw has to follow the direction field. So these solutions here at these points have to have a slope of 1. And then as you go further in, the slopes eventually of the slopes of the tangent lines to the curves eventually have to approach 0. So you see the direction fields allow us to draw solution curves for the differential equation without actually knowing the solution to the differential equation. Okay, that's the idea. That's the idea. Let's go back here. Let's go back. So for this little exercise, and this is you don't have to copy this down. This goes with exercises 3, 4, 5, and 6 from section 7.2. For this one, for A, which of the 4 choices, 1, 2, 3, or 4, would go with choice A?
3.
That's right, Claire. That's right, Mohammed. Choice 3. Now let's look at B. Let's look at B. Are there any questions on that? Okay, let's look at B. Let me go back to the whiteboard. Let me write down that differential equation. Okay, and I'm gonna clear this one. It's in the recording. Let's look at the y prime. Hold on here. One moment. Okay, let's look at y prime equals x times 2 minus y. Okay. And I will draw, I actually wanted it in black, good. Okay, so what values of x might be good to try here? Uh-oh, I kind of gave it away. X equals 0, right? Because if x equals 0, what's y prime going to equal? That's right, Jonathan, 0. And so if y prime equals 0, okay, well, now along the line x equals 0, that's the y-axis, right? That's the y-axis. So this means that if I put a bunch of coordinates along the y-axis, okay, each having x coordinate 0, the direction field tangent lines would all have to be flat, because that means a slope of 0. Okay. What would a good y value be?
1.
Well, look at your factors. What would be the easiest y value to use? You could use 1, but there might be
2.
something a little, I'm sorry?
2.
There we go. There we go. If y equals 2, there also, y prime equals what?
0.
That's right. So this means then that if we, like, if this is 2 here, say, and we plot some points, all having y coordinates of 2, the tangent lines are flat. So you see, this may give us enough information to be able to match this differential equation with one of the 4 choices. And when your homework, you're going to see problems, and they're multiple choice, problems. But you like you don't want to be plotting 100 different points and figuring out the slope for each of those points, right? You want to judiciously pick your values. And so I let x be 0, y equals 2, and then this is so far my direction field. Let me go back to the hold on, let me go back to the file here. Whoops, that's not the one. Hold on. Okay, so here's B. Okay, which of the 3 direction fields? That's correct, Jonathan. 1. 1 will be the right one. So you see, that's how you do these. That's how you do these problems. That's how you do these problems. So for B, it's going to be choice 1. See how that works? The graph number 2 here does have flat slopes along the vertical y-axis, but when you're at y equals 2, those points there don't have flat slopes. So whereas here along y equals 2, the slopes are flat. Does that make sense, class? Does that make sense? Are there any questions on that? Who's feeling good with that? Give me a thumbs up if you're feeling good with that. Okay, very good, Daniel. Very good, Clea. Hold on, some other people too. Very good, Avery. Okay, so that being said, thank you. Let me go into the ebook now. Let's explore a little bit more about section 7.2 in our last 10 minutes of class here. Okay. Okay, so let me bring this up here in the book, the ebook, section 7.2. So you see there, we have a direction field, and this is just a direction field for the differential equation x plus y. Okay, so what they did, and this is figure 3, section 7.2, they found a bunch of points and found and computed the values of the derivatives at those points, and then and then the tangent lines obey those derivatives, those slope values. And if we were to draw a solution curve on this for this differential equation, y prime equals x plus y, but the solution curve has to pass through 0, 1, it would look like that purple solution curve. So do you see how do you see how the solution curve obeys its tangents? If you think about like how many have been like maybe in a little river or something like that, and they're like, or one of those, I don't know what you call them, those little oh man, you float on them, the little tires or whatever, I forget what you call them, but I don't know if you've done any like rafting or canoeing, but how many notice you tend to go with the flow? How many have noticed that? If you're doing canoeing or rafting or tubing, I guess it's called tubing. Has anybody ever tried that, like on a body of water? Oh, reality town goes against the current. Okay. But if you were to just kind of let things go, you'd flow with the current, right? And you see how the solution curve just kind of flows with the tangent lines, doesn't go against them. The tangent lines represent the tangent lines are tangent lines to different points along the solution curve. The solution curves the solution curve obeys the differential equation, and therefore it has to obey the slopes of the tangent lines. It has to obey the tangent lines to its points along the curve. Okay, let's look a little bit more here. Let's go down a little bit. So in example 1, for instance, here they say sketch the direction field for this differential equation. Y prime equals x squared plus y squared equals 1. And this differential equation, it's not as easy as the ones we saw in the matching. So what they have to do is they have to pick some different coordinates, some different x, y coordinates, and find and compute the tangent or the value of the derivative at each point. And then they're going to draw tangent lines that reflect those slopes, those y prime slopes on the third line. Okay, so they just pick some points, and when you look at the figure 5, there's a picture of the direction field for that differential equation. And if we want a solution curve on the direction field, well, there it is. There's a solution curve on the direction field, and you see how the tangents there are tangent to the solution curve all along the solution curve. Do you see that? You see how the tangents guide the solution curve? And so without knowing the solution to the differential equation, you can draw solution curves once you know what the direction field looks like. Yes, Clea, question.
Yeah, so how do we know where, like in which part of the graph we do the solution curve?
So what'll happen is, like in WebAssign, it'll give a direction field and it'll say draw the solution curve passing through, like in this case, say the origin. Draw the solution curve passing through the origin. And so what'll happen is they'll give you like 4 different direction fields with 4 different solution curves, and you have to pick the one that looks right. The solution curve would have to pass through the origin, and it would have to obey the direction field. You see?
Yes.
See how that works? And they might even give you multiple points. They might say find the solution curves that pass through the origin and the point 1, 3 and the point -2, 4, and then you'll have 4 graphs with 3 solution curves on them each, and you have to find the right one. And since it's multiple choice in section 7.2, you have to be very careful. Okay, so good question, good question. If we go a little further down, okay, here's figure 8. And there they've drawn, well, how many solution curves do you see graphed on the direction field in figure 8? This is the direction field that goes with example 1. How many different solution curves do you see? 4? I think, yeah, 5. Yep, I agree. I see 5 of them. And, you know, we have a yellow and the green is a little hard to see. I see what you mean, Jonathan. So do you see how, like which solution curve, yellow, black, purple, green, or red, which solution curve passes through the point 0, 1? The black one. That's right. Do you see any other solution curves passing through the coordinate 0, 1? No, right? And it's because the solution's unique. Solution's unique. When you have a direction, when you have a differential equation and you have an initial value, that means you have a point where the solution, you want the solution of the differential equation to pass through that point. It's gonna be then a unique solution for well-behaved differential equations. Okay, who's reasonably comfortable with this? Who's reasonably comfortable with what you're learning here today from section 7.2? Okay, hang on here. There was Clay is, and somebody else chatted. Hold on, I'll see here. One moment. One moment, everybody. Well, I understand, Masume. It is going to take some time to get comfortable. Absolutely. It is going to take some time. And sure. Maybe I'll show you one more figure here. Let me keep going through here. See figure 11? There's another direction field for some differential equation. And you see the solution curves there? How they behave? They follow the direction field. That's why it's called a direction field. All right, are there any questions? I mean, just sort of questions in general on this? I know you need more practice, but how many of you feel, I'm feeling, at least for at first glance, this is making a little bit of sense to me. How many at least feel that way? Maybe give me a thumbs up. Okay, Jonathan and Clea. Mohammed, good, okay. Okay, well if there's no questions, let me stop the recording for this section 7.2. We're gonna do 7.2. We're gonna talk on Wednesday about Euler's method, and then we're gonna move into section 7.3 also. But I'll stop the recording here.